So yeah, my name's Harriet Fewster. I'm a statistician at R-HTA, and I'm going to talk to you today about a project I did with some of my colleagues at R-HTA about input correlation in PSA. So for some quick background, PSA is obviously a very common sensitivity analysis that's used in cost-effectiveness models. A key advantage of PSA is that you can explore the input of varying multiple inputs at once. But unfortunately, currently, inputs are often varied independently, even when there's evidence to suggest that they're correlated. So as a result, there's a suspicion that PSA results are systematically misestimating uncertainty. So why do we care? Well, uncertainty is a key factor for HTA agencies such as NICE when making decisions on treatments. So to investigate the impacts of input correlation, we made an example model. So this is a very simple 8-state Markov model, which is comparing a hypothetical treatment comparator. And we tried 3 different methods of accounting for possible correlation in this model. And obviously we used R and Shiny because I think that's got a really good balance of being easy to program on the back end, but then there's a user-friendly interface with Shiny for people who don't have so much familiarity with code. So I've put on the slide the parameters that we were varying, and then we used 3 different options for accounting for correlation. So no correlation, this was kind of your typical PSA. The only constraint was that we obviously constrained transition probabilities to sum to 1, otherwise everything was completely independent. Partial correlation, which is kind of mimicking the situation where you've got a paper that gives the correlation between your cost inputs and a paper that gives a correlation between your quali inputs, but you don't have information about correlation between costs and qualies. And then perfect correlation, this is where everything was correlated. We also tried to go for a worst case scenario here, so anything that we thought would improve the likelihood of cost effectiveness was positively correlated and then negatively correlated with inputs that we thought would decrease the likelihood of cost effectiveness, to kind of give the worst case scenario for where input correlation would change the uncertainty in the model. So now on to some of the R code. This is the cost function. So it's this is generating PSA samples of the single cost in the model, which is done via vectorization. So you can see that in the no correlation scenario, all of the costs are completely independently generated by applying a multiplier to the mean to create a standard error, pretty standard stuff. And then in the correlated scenarios, the cost is generated by applying a multiplier to the mean. The multiplier is pre-generated, so it's shared between different inputs. So this is what the Shiny model looks like. It's available now on the York website if anyone wants to check it out and see all of the different options. We have a dashboard layout using Shiny Dashboard. There's some options to kind of change some model parameters. You can make the model more or less complex by changing the number of health states and the number of costs per health state. You can also change the kind of overall level of variability in the model. You can also choose how many of the correlation options you want to run. And there's also some quality of life options, such as being able to just run the willingness to pay threshold without rerunning the whole PSA and being able to reset the model. So this is now the results after running the PSA in our base case. So as you can see on the table that I've zoomed in, all of the ICEs are actually really similar. So at 20K, which is the lower end of the nicest willingness to pay thresholds, all of the treatment would be found cost effective regardless of which option we'd decided to go with. But you can see there's a lot of variation in the net mean benefit and in the likelihood of net monetary benefit and in the likelihood of cost effectiveness. So specifically, like in the no correlation scenario, there's a 90% likelihood of cost effectiveness, and then in the perfect correlation scenario, that goes right down to almost 60%. And so if you look at the cost effectiveness plane, this is it zoomed in a bit, you can see why we think this is happening. So in no correlation scenario, all of the PSA points are very clustered, but in the partial correlation and the perfect correlation scenario, they are spread out, and that's basically the result of the higher likelihood of extreme scenarios that occurs when you add in correlation. You can kind of see like there are some much more extreme points in the correlated scenarios than in the no correlation scenario. So the final thing that we've included in this model was we then wanted to know which models were likely to be most affected by this, specifically in terms of the proximity of the ISA to the willingness to pay thresholds. So it's hard to vary the ISA, so we used the initial treatment cost as a proxy, and we reran the simulation for different initial values of the treatment cost. So, I mean, what we found out here was that in general, when we plotted the likelihood of cost effectiveness against the ISA for each of these runs, when the ISA was very close to the willingness to pay threshold, or when the ISA was very far away from the willingness to pay threshold, there wasn't very much difference in the uncertainty. So it's kind of that sweet spot at between 15K or 25K, where the ISA is moderately close to the willingness to pay threshold, is when we think this effect is most likely to be significant. So finally, to talk through some of the limitations of this approach. So we didn't include any alternative model structures. So for example, we could have used like a patient level sim or a decision tree, but we've instead just got the Markov model. So far our results only really apply to Markov models. Similarly, I mentioned earlier, we used a fixed multiplier to calculate the standard deviations for all of our inputs. This obviously simplified the coding quite a lot, but it meant that we weren't able to assess the effect of some inputs being much more variable than others, which I think often occurs in PSA. A third limitation was we only used one shape of scatter plot. So if you recall the cost effectiveness plane, our scatter plot was obviously kind of quite flat, and the points were stretching across the threshold. Obviously, if you tilted that scatter plot, you might find that the points actually would go parallel to the threshold, which might result in the no correlation scenario being seen as much less certain. So this is definitely a direction for future work to see how this effect changes for different shapes of PSA scatter plots. And then the final limitation that I want to just quickly mention, we didn't use real world data. We wanted to keep the focus more on the impact of correlation options. So we just, but obviously another direction for future work would be to explore these correlation options with some real cost effectiveness models. So now I'm just kind of moving back to the challenges of the R code. So I think one of the big computational challenges that we had was the PSA can take quite a long time to run, particularly the Explore tab. So we wanted a way to preload the base case results into the model. So R-Shiny does have a method of caching, which we looked into, but we were a bit concerned about obviously the impact on the amount of storage that we would be using on the University of York servers. So we actually did this manually. We saved the results of the model in an RDS file, and on the back end of the model, it checks whether the PSA button has been pressed. If the button hasn't been pressed, it shows the saved results. If the button has been pressed, it switches to the live results. Another big challenge, you saw the inputs page. There's a lot of ways to change the number of health states, the number of costs, the number of correlation options that are being run. And so we needed a very flexible code base that would handle this without having to code in every scenario manually. The two kind of big ways this was done. So on the back end, we used the per package to switch to a more functional programming paradigm. And then on to generate the plots, it was mostly a matter of being very intentional with the format of data that was being passed to ggplots. So we could use a long data format, and then you can use the grouping option and the faceting option in ggplot. So a fun fact about those plots is that there is no extra code for handling different numbers of correlation options. It's all done automatically by ggplot. Some final points, I think these are more just any kind of large-scale Shiny model, keeping the code base under control. This was a challenge. So the ways that we handled this was largely finding ways to reuse code. So there's only one module that handles transitions, costs, and qualies. Since all of those are basically the same kind of logic of display a table, allow the user to modify the table, and obviously check that their modifications are valid. So these were wrapped into a single module with some logic to handle obviously the differences between the error checking conditions. The other one obviously was, you saw some of the plots. All of the plots have a download button beneath them. So instead of copying and pasting the download button, it was, I wrote a generic kind of plot module, which adds the download button automatically. I think our Shiny modules are a really good way in general of kind of keeping down the amount of code that you're writing and keeping it in meaningful chunks. So the final thing obviously was sort of keeping the speed manageable. The main tool I found useful for this, I actually heard about this last year at R-HTA, was the micro benchmark package, which is really useful for just like running bits of code, seeing which of them are faster or slower. I would say the big wins that I then discovered with this were trying to obviously keep the amount of code in the loops to an absolute minimum, and sadly avoiding data frames and tibbles. We all love them for interactive work, but they're really slow on the back end, so switching to lists is definitely worth the pain. So yeah, that's everything. Again, the Shiny model is available on the University of York website. There's also a paper that is being published in Value in Health, which goes into a bit more depth about the methods that we used. Thanks very much for listening. I think there's some time for questions.
Yes, indeed. Thanks, Harriet. That was very clear, and thanks for keeping so well to time. So we've already got 3 questions coming in. So just starting with Dawn, who came first. How do you think these results might generalize to real-world examples? And Dawn saying she's generally seen variability reduce when accounting for correlation. And the second part of her question is, we don't usually have data on costs and utilities, how they're correlated, costs and utilities. What would you recommend giving this? So 2-parter from Dawn to start you off.
So I think for the first part, I think the issue is a lot of it is going to be about the shape of the scatter plot. We deliberately kind of chose a scatter plot that was going to create a big change in the amount of uncertainty. I think in a lot of cases, probably the correlations are going to cancel each other out. So there may be less impact, or there may be a reduction in impact. So it's more, I would say the point of this experiment is more to show that it's not necessarily, the effect's not necessarily going to go in one direction or the other. I think for the second part of the question, obviously you can't generate data that isn't there. But I would recommend doing sensitivity analyses. So if you don't have any plausible numbers, you have to assume independence in the base case, but possibly using sensitivity analyses for scenarios you think is likely would be a good way to make sure this effect is accounted for.
Great, thank you. Then a question from Shia, if I'm saying that right. Did you include a hierarchical relationship for quality of life for the health states? Any thoughts on this?
No, unfortunately, this was a very simple model. So from my understanding is the hierarchical relationship is you're constraining the amount of you're constraining the quality of life. So a health state that's rated as worse can never have better quality of life than a health state that is rated as better. Is that right? I think that's obviously a very good way of accounting for this effect. Obviously, it's not going to completely solve all of the problems because it only kind of like puts a lid on how much correlation that is being ignored rather than completely removing it. So that's my take, I guess.
Okay, thank you. And a question from Frank. Does the skew in the mean result mostly or all come from fitting gamma log normal distributions to the health state course? And were there any asymmetries on the effect side? And is it possible to see the breakdown?
Yeah, I think it's likely because we were using skewed distributions. I think, often we're working with inputs that are skewed, so I don't think using normal distribution is a particularly, so I think it sort of might reflect reality using a skewed distribution for inputs that are constrained to be greater than 0.
Okay. And question from Alfredo. How were loops minimized? Did you vectorize the PSA? And was minimizing the loops also the reason for using a single module for transitions, coasts, and qualies?
So no, loops were minimized largely just by, for example, that multiplier, making sure that was calculated as early as possible, making sure that any operations like data cleaning operations were being done outside of loops. PSA was vectorized. I think that's a really good way of speeding up code in R. Obviously, vectorization is a really powerful tool we're given out of the box, essentially. And the single module was more about just reducing the amount of code that was written. It's actually, obviously, it's 4 copies of the same module, but it recycles a lot of the logic, and it meant that when we were making changes to like the UI, we could make 1 change rather than 4 changes. So it was more to streamline things on the coding side rather than the running side.
And if I can just ask a follow-up question, you mentioned avoiding tables and data frames for the shiny bit of things. What was the relative computational burden if you had stuck with those as compared to lists? Would it have been completely unworkable, or would it just been extremely slow, or something in between?
It would just have been extremely slow. I think when I was doing speed tests, it was easily a factor of 10 or possibly more when I was running it. And I think particularly when you increase the number of iterations, I would assume it would just, the amount of time that you would increase the runtime by would increase even more.
What was the package you heard at last year's or for HTA that helped you? Was this
Micro benchmark.
Marker benchmark? Okay, I'll make a note of that as well myself. We've got time for one last question for Harriet. Any takers?
Oh, thank you.
Yeah, Rob has helpfully just put micro benchmark in the chat for anyone who's interested. Do you have any plans to take this further, Harriet? Will you be extending this and generalizing it, or was this sort of a discrete project?
It's currently a discrete project. If we've got time in the future, it would be I think it'd be really interesting to continue it, but there's no plans at the moment.
Yeah. it always kind of pricks my conscience when I'm not doing correlated input parameters in PSA, but it'll be nice if there's guidance. So it's really helpful that you've presented that. That's fantastic, Harry. Thank you very much. So
Thank you.